Assalamualaikum warahmatullahi wabarakatuh. Hello everyone, my name is Lakshman Mahadar. With the student ID 2024. Today I would like to present my practical report on the machine learning course, where today I do two practicum, that is neural network and Q learning. First one yeah, is the neural network practicum that in here I built an artificial neural network to predict building energy efficiency. For this project, I utilized the energy efficiency dataset, which examines how different architectural shapes affect energy consumption. The dataset consists of 768 samples with 8 structural input features labeled as X1 through X8. This includes attributes like relative compactness, surface area, wall area, and overall height. Well, in here, first, I install a library that named TensorFlow for because in this practicum, in the neural network practicum, I use the TensorFlow library to do the practicum. After I install the TensorFlow library, I importing the library that I use in this practicum, and then after importing that, we do the exploratory data analysis. Because before we diving into the model architecture, it was critical to understand the underlying patterns and a relationship within the data. I conducted an exploratory data analysis or EDA and visualized the feature relationship using a correlation matrix heat map in here. From the heat map analysis, we discovered several height impacts inside. First, overall height X4 and relative compactness or X1 exhibit a very strong positive linear correlation with both heating and cooling loads. This indicates that taller, more compact circular design inherently require higher thermal energy capacity. Second, roof area or X4 and surface area X2 displayed a strong negative correlation with our targets, meaning they move in opposite direction. Interestingly, features like orientation X6 scored near zero, suggesting that the direction the building faces the negligible linear impact on energy consumption within this specific dataset. This preliminary phase proved that architectural geometry heavily dictates energy demands, validating our approach to use these features for predictive modeling. And then we moving on to the data processing. In here, first, I programmatically check for any missing or null values using this is the using the TF that is now our dot sum function. The dataset was completely clean, so no data imputation or row dropping was necessary. Second, the dataset was split into a feature matrix X and the target matrix Y to properly validate our model's ability to generalize to unseen data. I applied an 80-20 trend test split. 80% of the data was allocated to train the network, and the 120% was strictly reserved for evaluation. Finally, because neural networks are highly sensitive to features on completely different numerical scales, for example, like comparing relative compactness values under 1.0 to surface area values over 500, I applied feature scaling using size-skewed-learn standard scale. This transforms the input dimension so that they all share a mean of 0 and variance of 1 effectively neutralizing scaling bias and accelerating model confidence. Now let us discuss the core engine of this project, the multi-layer perceptron architecture implemented using TensorFlow and kernels. The model is built using a sequential topology consisting of four distinct layers. The input layer directly ingests the eight standardized architectural dimensions. Hidden layer 1 contains 84 neurons utilizing the ReLU or rectified linear unit activation function. And ReLU introduces nonlinearity, allowing the network to learn complex non-set boundaries. A dropout layer is positioned immediately after with a rate of 0.1. This means the network randomly deactivates 0% of its neurons during its training step. It is a highly effective regularization technique that prevents the model from over-memorizing the training data, thereby mitigating overfitting. Hidden layer 2 consists of 32 neurons, also utilizing the rally activation function to further refine feature extraction. The auto layer features exactly two neurons with a linear identity activation. The specific setup is what allows the network to execute joint estimation, outputting both heating load and cooling load predictions simultaneously. For the training configuration, I selected the Adam Optimizer for its adaptive learning capabilities and mean squared error or MSE as our last function. The network was trained over 150 epochs with a bond size of 16 keeping aside 20% of training data purely for real-time validation. In here we can clearly see the epoch time from the 1 until the 150 epoch. Alright. Lastly, let's look at the evaluation metrics and final outcomes. To quantify the precision of our model, I calculated the R squared score, or the coefficient of determination on the independent test set. The model achieved exceptional performance, yielding an R squared score of approximately 90% or higher for both heating and cooling load prediction. Looking at our Looking at our physical port, the loss curve demonstrates a smooth exponential decay for both the turning and validation lines converge gracefully. The absence of a wide gap between them confirms that our model is well fitted and robust against overfitting. The actual versus the predicted scatter plot shows that our data points closely aligned with the ideal y to equal to x diagonal line, proving highly predictive accuracy. In conclusion, this practical was successfully demonstrated an artificial neural network can accurately map structural building parameters to thermal energy demands. In the real world, this model serves a powerful predictive tool for architects and civil engineers. Also, it can ultimately save you substantial operational energy costs. Well, that's for the first practicum. Now let's move to the second practicum, that is Q-learning. In here, of course, first we set up the import library and we importing the library that necessary. And let us first discuss how the environment is structured. We scaled up the initial 6 by 6 maze into an 8 by 8 grid, which drastically expands the complexity of the problem. This grid yields a total state space of 64 discrete states, indexed linearly from zero at the top left corner, which serve as our starting point, to 63 at the bottom right corner, which is our designated code state. To map the agent position from a two-dimensional coordinate column, column into a single flat index, we use the formula as equal to R times and columns for C. Formula or action space A consists of four deterministic uh, movement up, down, left, and right. The key challenge here lies in the obstacle handling mechanism. We incorporated a dedicated static set called walls. During the state transition function, if an action directs the agent into a coordinate registered within the set, the system triggers a revert mechanism. The agent bounces off the wall. Its next state remains identical to its current state, simulating a physical barrier. Now let's move into the core mathematical engine of the simulation. The Q value update rule. The brain of our agent is Q table, uh, represented as 64, yes, as the 64 by 4 matrix. 64 by 64 by 4 matrix, completely initialized to 0, completely initialized to 0. This signifies that at the beginning of the training phase, the agent is entirely blind to its surroundings. The learning process relies heavily on the Bellman optimality equation via temporal difference learning. Uh, we configured for this 8 times 8 maze. For alpha, our learning rate is set to 0.8. Yeah. Oh, yeah. Towards alpha vision 0.8, this hard value ensures that the agent aggressively prioritizes new incoming information. And the second gamma is this constructor is set to 0.95. Alright. And then in here we have the exploration and exploitation strategy where we balance where we set the exploration prop and or epsilon to 0.2, and because we expand the maze to 64 states, we increase the training cycles to 3000 people. Yeah, in here we to 3000 people and allow to the maximum step per people. And then finally that's it. And then finally let's analyze the testing phase and the visual outcomes. Once the 3000 people are completely, we turn off the exploration entirely, setting epsilon to 0, forcing the agent to act purely rationally. And as you can see, from the terminal output, the agent successfully navigated from state 0 to state 63, executing the absolute minimum number of steps required without a single collision. Looking at the generated matplotlib heat map, we can observe the gradient of the maximum key values. The cell closer to the goal state display as much darker, intense to the red-orange gradient. This visualizes the propagation of the reward backward to the state. The cells marked with an X represent the walls, and they remain completely blank or zero because the agent policy learns to entirely avoid transitions into those states. Well, that's all for today's practical. Thank you for your time, and